So now we'll move towards thermal modeling. As I stated earlier, this is just a surface heat flux. If you see here, so just surface heat flux as I see here. But due to heat transfer phenomenon, heat may transfer in the width direction or in the depth direction. Convection is possible, radiation is possible, and this is a very high temperature laser beam. Or ambient temperature is always available, so convection is also possible. So all three modes of heat transfer will be active as your moving heat source is there. So for accurate modeling, I should consider this 3D heat equation so that my temperature is a function of, and that too transient, it's not a steady state. So my temperature will be function of x, y, z and t, time. Because it is moving, the whole process is dynamic. With the time, your temperature distribution will vary inside the workpiece. So that's why we have taken the 3D transient conduction equation. That is very famous, well-known equation. So most of the constant, if I will tell you this T temperature is a variable, that is a function of coordinates x, y, z and time t. And some material parameters are there like a density, specific heat and conductivity. That is again material parameter, depend on the material you will get this data. This term is extra, right? If you are thinking from your textbooks, your basic heat transfer textbooks, only this much part of the equation you might have seen. So the last part, that is V dou tau by dou x, is coming from the moving heat source. Our heat source is not stationary now, it is moving with the velocity V. So that will affect temperature distribution in the x direction. So that partial derivative should come into picture. So from subroutine point of view, you need not care about this. Our Fe will take care of this velocity and the temperature distribution. But theoretically, you should be very clear. If somebody will ask you how your heat conduction equation will change in context of moving heat source. So theoretically, this term should be added, and if you are theoretically writing your code in MATLAB or let's say in some other programming language, so this term should be there, then only we will get some accurate results. As far as FE software is concerned, that will take care of this velocity and moving heat source because we already selected transient heat transfer analysis. So all this transient phenomenon, that is velocity is your function of time, automatically it will take care. Okay, so this is the understanding of your governing equation. Now, this governing equation should be constrained with some of the initial and boundary conditions. As I said, your temperature is a function of x, y, z and time t. So at initial condition, the whole model should be at the some initial temperature. Mostly that will be room temperature. Whatever, depend on your ambient condition. If you say your ambient condition is 25 degrees Celsius, fine. If you are doing this experiment in let's say some hot chamber, so maybe your initial condition will change accordingly. But this initial condition you should state and that you should apply in your FE model. Apart from that, boundary condition, as I said at the same time the convection and radiation will be active and your heat source, that is a heat flux Q, is there. And if I will show you, this is the Z direction, right? Z direction. So a heat flux is going to apply like this. So our Fourier law says Q is minus Ka times dt by, in this context, your heat is going to transfer in Z direction as your heat flux going to apply from the top side, so along the Z direction. So this is the one condition, but at the same time, your convection and radiation will also be active. So minus Ka dt by dz, this term. Okay. So don't worry about area. Again, this will be again taken care by the element size in the finite element analysis. So at that instant, which element is carrying heat, it will take care. Okay. So this term Q, and this is the convection, H times T minus T naught. So convection is depend on the heat transfer coefficient H. And this temperature T continuously vary based on your solution. T naught is the sink temperature, we call it as, or that is ambient temperature. The ambient condition we already stated here, T naught. So same T naught will take care your convection. So to apply convection, you should know the value of heat transfer coefficient H. And finally radiation. So the constant sigma, so don't confuse with the stress. This is the constant sigma, we call it as a Stefan Boltzmann constant. So that is well known constant, already known value. Emissivity again depend on the material and many other factors, whether the body is black or grey or what kind. Again, this kind of information you will get in the literature. And this is famous Stefan Boltzmann constant law, sigma epsilon times T raised to 4 minus T naught raised to 4. So in radiation, the heat exchange will happen with the fourth power of the temperature. So these three, conduction, convection and radiation, will act simultaneously, and we can define surfaces on what surfaces we want convection, what surface we want insulated. That we can define in the Abaqus model. Let's say we want only convection at the top surface and other surface will be insulated. We can do it. So accordingly, that boundary condition equation we can define for all surfaces or for the whole model at once. So where we are stating that boundary condition, you should be very clear. Let's say surface heat flux is only applied on the top surface. So we'll select only that top surface for the heat flux. If the convection, let's say you are applying on all 6 surfaces, while applying film coefficient in the Abaqus, select all that 6 surfaces and you will apply convection. So that model will take care where convection is applied, which surface is insulated, or whether you want to consider radiation or not. So as a researcher, as an engineer, understand your physical situation, you can delete some of the boundary condition if you want. If you don't want radiation, you can just discard this, no issue. And accordingly, you can select your initial and boundary condition based on your requirement. So, okay. So, as I told you, I will show you two things or two kind of subroutine, let's say. The purpose is same, to model moving heat source, but in Abaqus there are two main solvers are there. Abaqus standard, which work with implicit method, and Abaqus explicit. The name itself suggests that works with the explicit method. So this, what are the advantages of two solver, when to use which solver, that is a separate topic actually. We will not go in that much detail. But in our context, I will tell you, whenever a model consists or simulation consists lot of non-linearities, dynamic phenomenon, contacts, damage, such kind of complex things, it's very difficult to handle with the implicit algorithm. And mostly such kind of very fast wave propagation phenomenon involving material non-linearity, and the contact nonlinearity. Engineers, scientists prefer explicit method because that will converge your source.